Hey guys, so today we're going to start Unit 8 Acquisition 2, which is describe chemical equilibrium and apply Le Chatelier's principle to a system at equilibrium. So a few things that you should be able to do for this acquisition. First, use the principles of kinetics and collision theory to describe equilibrium. Write equilibrium expressions for a given reaction. Use molar concentrations of reactants and products of a reaction at equilibrium to calculate the equilibrium constant for the reaction. So we're going to focus on A, B, and C today. Later this week we will determine the type of stress on a reaction and predict how that stress will affect the reaction. Alright, so today, chemical equilibrium. Chemical equilibrium occurs when the forward and reverse reaction proceed at equal rates. So that's really important. This is going to occur at equal rates. Equilibrium does not mean that we have the same concentration of reactants and products. It means that the forward and reverse reaction are proceeding at equal rates. So that means that the rate of products formed will be equal to the rate at which the reactants are formed. Since they're occurring at equal rates, that means that our concentration will no longer change with time. So the two graphs at the bottom are showing a reaction at equilibrium. So the first one is showing what happens to the rate of reaction over time. So when we looked at calculating rates of reaction, we saw that the rate of reaction is going to decrease over time. So going back to collision theory, we know in order for reactants to form products, those reactants need to collide. Well, what happens is as that reaction proceeds and we have more collisions, there are less reactant molecules available to collide. So as we have less reactant molecules available to collide, that reaction is going to proceed slower. So we see that the forward reaction, the rate of reaction is decreasing over time. The reverse reaction is going to increase over time because we're making more products. More products we have, those products can collide and then form the reactants. So we see that once they are at an equal rate, we are at equilibrium. But again, that's looking at the rate of reaction. The bottom graph is showing concentration over time, or the amount over time. So again, reactants are going to decrease over time, products are going to increase over time. This is like our little fish graph. And we see that we reach equilibrium where we no longer have a change in concentration. Alright, let's talk a little bit about the forward reaction versus the reverse reaction. So some reactions are reversible. So all that means is that the products can go in the reverse direction and make the reactants. So looking at this reaction here, N2O4 produces 2 moles of NO2. So the forward reaction is if the reaction proceeds as written. N2O4 produces 2 moles NO2. Well, this reaction is reversible, and we know it's reversible because I see that double-sided arrow. So that means this reaction can also go in the reverse direction. So that means that the products can reform the reactants. So in a reversible reaction, these two reactions are constantly occurring. It's not static equilibrium. It's not like we reach equilibrium and nothing is happening. Our forward reaction is continuing to occur, the reverse reaction is continuing to occur, but they're happening at equal rates. If it's happening at equal rates, we're not going to have a change in concentration. Alright, KEQ, our equilibrium constant. This just quantifies the position of chemical equilibrium. So we can calculate our KEQ, and based on that number can give us some information about equilibrium. So important that we remember this, and in a little bit I'll show you guys an easy way that you don't have to memorize this. But if you calculate KEQ and that number is less than 1, it means the reaction favors the reactants. If you calculate KEQ and it's greater than 1, the reaction is going to favor the products. Kc is just like KEQ. It is still an equilibrium constant, but since it's K sub C, that C is for concentration. So this is just the value obtained when we use molar concentrations to represent equilibrium. So how do we calculate our equilibrium expression? Well, the equilibrium expression is going to be products over reactants, and we're going to raise each of those to the power equal to its coefficient. So KEQ is going to be equal to the concentration of our products over the concentration of the reactants, each raised to the power equal to their coefficient. So if you think about this equation, you shouldn't have to memorize your KEQ value. If you have more products, that means the numerator is going to be bigger. If you have a bigger number divided by a smaller number, KEQ would be greater than 1. So KEQ is greater than 1, it's going to favor the products. If you have more products, numerator is bigger than the denominator, KEQ would be greater than 1. And then same thing if KEQ is less than 1. Let's say the reaction favors the reactants. You have more reactants. If the denominator is bigger, a smaller number divided by a bigger number, KEQ would be less than 1. So if you just think logically about the equation, you shouldn't have to memorize this point over here. All right, so 2 examples. We need to write a KEQ expression for this reaction. So KEQ is going to be equal to products over reactants. So again, products are on the right side of the arrow. So my product is ammonia, NH3. I'm going to use brackets to represent the concentration of it, and I'm going to raise it to the power equal to its coefficient. So its stoichiometric coefficient is 2, so I'm going to raise it to the second power. Divided by the reactants, each raised to the power equal to their coefficient. One really important thing to remember for equilibrium expressions is that we multiply. If you have more than one reactant or more than one product, we multiply them together. And hydrogen has a coefficient of 3, so I would raise it to the third power. So that is our equilibrium expression. All right, pause the video, try the second one on your own. When you're ready, unpause and check out how you did. KEQ is equal to products over reactants, so my product O2 oxygen raised to the power equal to its coefficient, divided by reactants, each raised to the power of their coefficient. All right, next, another important fact to remember. Pure solids and pure liquids are not included in the equilibrium expressions. The reason they're not included is because they don't affect the concentration. A solid or a pure liquid is not going to affect concentration, so we don't include it in our KEQ. So let's say I had this reaction here. Anything that is a solid or a pure liquid is not included in the KEQ expression. So I'm just going to cross those out, and now I'm going to write whatever is left over. Products over reactants, so calcium chloride times the concentration of carbon dioxide, all over my reactant. So I have one reactant left, HCl, hydrochloric acid. And again, I'm going to raise it to the power equal to its coefficient. All right, grab a calculator, let's do some math. Next example, calculate KEQ for this reaction, and this time we are given our equilibrium concentrations. So the first thing that we have to do is write our KEQ expression. KEQ is equal to products over reactants, each raised to the power equal to their coefficient. And we have our molar concentrations at equilibrium, so all we have to do is plug in those values and solve. And I would get 0.211, keeping 3 significant figures. There is no unit for KEQ. Alright, follow-up question. Does this reaction favor the reactants or products? This one would favor the reactants. And we know that it favors the reactants because KEQ is less than 1. So going back up to what I have started, if KEQ is less than 1, it favors the reactants. Alright, last example. Again, pause the video, try the second one on your own. When you're ready, unpause and check out the answer. Calculate KEQ for this reaction, again, given molar concentrations at equilibrium. So we actually wrote the KEQ expression for this reaction already, but I'm going to rewrite it just so we have it and we can see what we're doing. So products over reactants, each raised to the power equal to their coefficient. Remember, if you have more than one product or more than one reactant, we are multiplying those values together. Alright, so all we have to do once we have our KEQ expression is just plug and chug. So I can take my molar concentration of ammonia. I'm going to raise that to the second power, divided by the molar concentration of nitrogen, times the molar concentration of hydrogen to the third power. And you should get 0.083. And then follow-up question, does this reaction favor the reactants or products? So again, here is another example where at equilibrium, this reaction would favor the reactants. The reason we know it favors the reactants is because KEQ is less than 1. And again, don't memorize that. Think about it logically. KEQ is equal to products over reactants. So in order for KEQ to be less than 1, the denominator has to be bigger, which means we have more reactants at equilibrium.